That's why I don't mind people.
Okay, let me introduce our speaker today, Dr. Vuong Phan. He received his PhD degree in mathematics from Vietnam National University in Ho Chi Minh City, and then he became postdoc at several places in Luxembourg, and then in Vienna, Austria. Now he is a lecturer at the University of Southampton, and today he is going to talk about the boosted difference of convex functions algorithms. Now it's yours.
Thank you, Mings, for the very nice introduction. And firstly, I would like to thank the organizer for your kind invitation. So it's my pleasure to be here to give a talk at the Variational Analysis and Optimization webinar. So I have had the chance to meet most of the organizer except Alex and Vera, I think. So
you will probably have a chance, hopefully.
Yeah, I hope to visit Australia as soon as possible and to meet you in person. So my talk today will be about the boosted DC algorithm, which is a joint work with Francisco. So I suppose that most of the optimizer in Australia are familiar with Phan, because he spent 2 years in Newcastle with John. So here's the picture took in Luxembourg in 5 years ago, I think, where we did the postdoc at the University of Luxembourg. So the joint work started like 5 years ago. So here's the outline of the talk. So after a short introduction, I will go to the boosted DC algorithm. So we denoted by BDCA. So the key idea is to add a line search step to the classical DC algorithm. And then we will talk about the convergence and convergence rate under the KL properties. And then in section 3, I will present some numerical experiments. Firstly, the DC problem in biochemistry, where we start the story, and then 2 more applications in machine learning. So let me first start with the introduction about the DC programming. So in this talk, we will consider non-convex optimization problem, minimize phi of x, which is the difference of 2 convex functions, g and x here. Okay, so g and x are a convex function, and we assume that the objective function phi is bounded from below. So in principle, this is a NP-hard problem, right? Because for example, if you think about minimize a quadratic objective function where the matrix is indefinite over a box constraint, that's already a NP-hard problem, right? And in principle, any C2 function is a DC function. So just to emphasize that is a difficult problem, but this is somehow close to the convex community. So 2 weeks ago, I think, where Rosin present an algorithm for minimizing the ratio, right? So if the numerator and denominator are both convex, then we can reformulate at the DC problem in the fractional optimization. So let me make some assumption on the problem we are considering. So firstly, we can assume that both G and X are strongly convex. Otherwise, we can add a strongly convex term like rho over 2 and norm of x squared to both sides of the objective, both sides of G and X, and we obtain the difference of two strongly convex functions with any modulus rho. We also assume that the first function G here is smooth, okay, on an open set containing the domain of H. And the second function, the concave part, is subdifferentiable. So here's the first order necessary optimality condition, basically saying that a point x star in domain of phi is an optimal solution, then the subdifferential of x and x star is singleton, so it's equal to the gradient of g at x star. And we also say that x bar is a critical point of this problem P if the gradient of g at x bar is an element of the subdifferential of x and x bar. So we see that the point x star satisfies the first order necessary optimality condition, then it's a critical point, but the converse is not true in general. Here we have a simple example where we have the function phi from Rm to R defined by this formula. So the function g is here smooth and x is non-smooth. Here is a figure in R2. Okay, so phi will have a 2 power m critical points, but it has only one point which satisfies the first order optimality condition, which is also the global minimum of phi. So here in this figure, the green point is the global minimum, and the other 3 red points are the critical points. I summarize some previous work on minimizing the difference of convex function. The first one was done by Fukushima and Mai in 1991. So actually, he did minimize the sum of g of x and a smooth function, any smooth function. So it's more general than just the DCA problem here. So the first function g is strictly convex and can be non-smooth, and the second function x is smooth, but can be non-convex. Okay. And in this case, x star is a local minimum, then the gradient of x and x star is an element of the subgradient of g. So here's the algorithm of Fukushima and Mai. So the idea is very simple because the objective function is non-convex. So at x step, we will convexify the objective by replacing the non-convex part by its linear approximation. So here we replace h of x by its linear approximation, the gradient of x and xk times y. And solving the sub-problem, which is strictly convex here, we will obtain the unique solution yk. And if yk equal to xk, we stop because we obtain the critical point. Otherwise, we perform an ambiguous backtracking from xk with the trial step psi lambda k equal to 1. So actually, this one is very close to the modern proximal gradient algorithm. If we add here a proximal term 1/2 y minus xk squared and so on, then we obtain the classical proximal gradient. algorithm. And then after the Armature backtracking, we take xk plus 1 equal to xk plus lambda k dk. The second one is the DC algorithm, difference of convex algorithm, proposed by Phan, Letty, and their collaborator in 86. So the idea is also very simple, just linearize the non-convex part. And we noticed that the DCA can work for both function g and x which are non-smooth. And in this case, the critical point is defined by this quantity. The subgradient of x star of x and x star is a subset of subgradient of g and x star. And here's the DCA algorithm. We take u belong to subgradient of x and x star, and then solving the subproblem here, okay, which is a strongly convex subproblem, obtain yk, and then just simply take xk plus 1 equal to yk. Okay, so the idea is the same with Fukushima and mine, just linearize the non-convex part. So this step is equivalent to solving the dual problem dk here. So x star here is the classical conjugate of x. And just to emphasize that the DCA algorithm can work for g and x, we can be non-smooth. And in the DCA, we just simply take xk plus 1 equal to yk. So which is similar to Fukushima and mine with lambda k equal to 1. So we have a proposition saying that for if g and x are strongly convex with modulus rho greater than 0, then we can prove that phi is with the objective value of the function at yk is less than phi of xk minus this quantity, rho the norm of dk square. Okay, for where g is smooth, or when the x is smooth, and we have this property, which is saying that if the constant alpha here in the Lyser is less than rho, rho is the strongly modulus constant of g and x. In principle, we can take it as big as we wish, right? In that case, the Fukushima algorithm and DCA algorithm are the same, okay? Because this inequality, the inverse one, less than or equal, we always satisfy with lambda k equal to 1. So why the FM, the Fukushima mine, and the DCA work? And the Fukushima mine work because we can prove that the dk, which is equal to yk minus xk, is a descent direction of the objective function at xk. And the DCA work because we have the decreasing in the objective function by the previous proposition. So the advantage of FM and DCA is that it's very simple. The idea is very simple. It's work well in practice, and DCA does not require any laser. But the drawback is that it's very slow in practice. So we recognize this one when we did a numerical experiment in the application in biochemistry 5 years ago. And the question is that can it be accelerated? And the answer is yes. But the payoff is that we need to require that G is smooth. And thanks to the fact that the directional derivative of phi now at the yk with respect to direction dk is less than 0. So basically that we can prove that dk is not only a descent direction of the objective at xk, but it's also descent direction of the objective at the new point yk. So and there are two principles for any algorithm for optimization problem. Is the first one. The first step is you try to find a descent direction, which is usually very expensive if the objective function is non-smooth. And as long as you have a descent direction, we try to follow that descent direction as fast as we can, right? And the classical technique is the laser. Moreover, the DCA can be not only slow, but easily get trapped at the global minimum at a critical point. Here, we revisit the previous example in R2, okay? So in this example, we have G here and H here. G is smooth and H is non-smooth, and we have 4 critical points. The green one is the global optimal, and the 3 other red points are the critical points, and also the local minimum, local minima. Okay. And here, if we start DCA at x0 at this point, for example, after one step, it sends you to the point y0, which is xk x1, right? And eventually it sends you to the local optimal 0 and -1. But we, if we have the property that the direction dk, d0 in this case, which is y0 minus x0, is also a descent direction of the objective at y0. It means that from here, the point y0 here, we can go a little bit further. Okay, we can go a little further, for example, to this point, which is in the neighborhood of the local of the global optimal. Then eventually we have to the global optimal. So that is the key idea of the boosted DC algorithm. So we can prove that if G is differentiable, then the directional derivative of the objective function phi at yk in the direction dk is yk minus xk. Okay, it's less than or equal to rho norm of dk square. Rho is the modulus of the strong convexity of G and H. And actually the proof is very simple, so that I can present it here. Here's the definition of one side derivative, right? So phi prime of yk at dk equal to this formula. And because G is smooth, we can replace this one by the gradient of G at yk times dk. And this one can be replaced by VDK with any phi belong to the subgradient of x at yk, thanks to the convexity of x, right? And also because yk is the solution of our subproblem, the optimality condition saying that the gradient of g at yk, which is equal to uk, must belong to the subgradient of x at xk. And because x is strongly convex, the subgradient of x is strongly monotone, right? Which content with the same modulus. And by the strongly monotone, the strong monotonicity of the subgradient, we have this this inequality. And then just substitute these two to the first inequality, we obtain the proposition. And then if we have the descent property, then the next step is very simple. We just add the line search from yk. So here's the formal statement of the BDCA. The first step is similar to the DCA. We take UK belong to the subgradient of x and xk. So basically this step is convexify the objective function. So the subproblem to obtain yk. And if dk equal to 0, we stop because we obtain the critical point. If not, then we take any trial step size lambda k bar and perform the line search by checking if this inequality is satisfied or not. Okay, if this one is we need this one less than or equal to phi of yk, and if not satisfied, then we reduce the step size. Okay, and then we take xk plus 1 equal to yk, which is the point computed by DCA, plus lambda k dk. It's better to illustrate it by a simple example. So we have seen before that if we start here, then there is DCA after one step send you to the point y0, and after 5 steps it sends you to the local optimal. But for the BDCA, so this is x0, this point is y0, and after a line search step, it sends you to this point, orange point, which is in the neighborhood of the global optimal. And in 2 iterations, it sends you to the global optimal. If we take this point, this starting point, for example, the same situation, the same phenomena happen. After 4 steps, the DCA gets stuck at the local optimal. But for the BDCA, after 1 step, it can escape the local optimal here, and it sends you to this point, which is in the neighborhood of the global optimal again. Here's the same situation. Okay. So to finally, if we take the starting point in the neighborhood of the global optimal, then both BDCA and DCA send you eventually to the global optimal. But here, for example, DCA take 4 or 5 iterations, and DCA take only 1 iteration. So to show that the previous starting point was not chosen on purpose, we have select here 1 million random starting point in this area, and we count the number of the sequence converging to its 4 critical points. And here you see that the DCA is converge to the 4 critical points almost equally, 25% to X point, while the BDCA send you 99.6% to the global optimal. So feel free to interrupt me if you have any question, okay? You may wonder why we need to restrict our analysis for the case she is differentiable. We also ask ourselves if the BDCA also work when she is non-differentiable or not. And the answer is negative, unfortunately. So here's an example where we have G is non-differentiable and X is differentiable. And if we start at the point X0 is 0.5 and 1, then the point generated by DCA is Y0 here, is 1, 0. And this one, D0 is not a descent direction of the objective function phi at Y0 anymore, okay? So it doesn't work. So the advantage of BDCA is that it's faster than DCA, is help us to escape the local optimal. But the class of object of function to minimize is smaller because we require she need to be smooth. Nevertheless, it's true in one-dimensional space. So if the function g is g and x in one-dimensional space, then we can prove that the directional derivative of phi at yk with respect to direction dk is still a descent direction of the objective function. Okay, so here's the convergence analysis of BDCA. So the convergence analysis is quite classical and based on the technique present in the paper of Artut and Bol. And we need to adapt the Kurdyka Lojasiewicz property. So the first theorem saying that phi of xk is decreasing and converge to some phi star. That's it clear from the property of the algorithm, right? And any limit point of xk is a critical point of our problem P here. And if phi is cohesive, then there is a subsequent of xk converges to a critical point of our problem. And furthermore, the series dk square is summable. And if the step size lambda k is bounded from above by some lambda bar, then this series is also summable. The difference of xk plus 1 and xk square. So for the convergence of the whole sequence, we need the Kurdyka Lojasiewicz property, which defined as follows. So the function f is local Lipschitz function, and we say that f is satisfied. Here I need the strong Kurdyka Lojasiewicz property. If there exists eta and the neighborhood u of x star and the concave function phi such that these 4 conditions are satisfied. The most important one is the 4th condition, saying that the derivative of phi at fx minus fx star times the distance between 0 to the Clark subdifferential of f at x star is greater or equal than 1. So 2 weeks ago, you see the Kurdyka Lojasiewicz property presented by Ting Kai with a specific function phi. Here I need to use the strong. The strong here is because in the classical definition of Kurdyka Lojasiewicz, this is the limiting. This is the limiting subdifferential. Subdifferential. So we need to use the Clark subdifferential, which is a little bit bigger. I will explain later why we need to use the Clark, but not the limiting subdifferential. So here's the convergence theorem. Let's xk is generated by the BDCA. And suppose that xk has a cluster point x star, and we need also the gradient of g is locally ellipsis. And if the objective function phi satisfies the strong Kurdyka Lojasiewicz inequality, then the whole sequence xk converges to x star, which is a critical point of P. The proof is technical, but it's become standard nowadays. And just to mention that the step size lambda k can be 0 or unbounded. So if it's 0, then it's coincide with the DCI. But in practical, it can be increased very aggressively. We need to assume that phi satisfy the strong Kurdyka Lojasiewicz inequality, or the function minus phi satisfy the classical Kurdyka Lojasiewicz inequality. The problem is that we need to take the minus outside of the subdifferential. So it's a technical assumption, because in the proof we need to take the sign minus here outside of the subdifferential, and it's only satisfied for the Clark subdifferential. And with a specific function phi, for example, in this case, if phi t equal to mt1 minus theta for some theta belong to 0 and 1. So this one is was used by Vojins 2 weeks ago. That we have the convergence rate. If theta equal to 0, then we have the finite convergence. If theta equal to 0 and 1/2, and we have linear convergence. And if theta from 1/2 to 1, then this is a sublinear convergence. Okay, any question on this one?
If I can, I have a small question. So
Yes.
you're using this, so what you call strong KL inequality, using Clark's subdifferential. Do you have examples showing that the conventional KL inequality is not sufficient?
No, I don't. So it's also can be true with the classical KL, but we don't know how to prove that. Or we need to assume that the function minus phi satisfy the classical KL inequality.
Yeah, I understand that. I just wonder if there are examples showing that indeed this version is needed and the traditional is not sufficient. Okay,
we
thank
don't
you.
have we don't have such an example in our paper. Yeah, but that's an interesting question.
Okay, good. Thank you.
And I think Boris suggests to have a look at something like using his new development on the, I don't know, the symmetric or something differential, but we haven't time to have a look at that.
Okay.
So now come to the question how to choose the trial step size lambda k in our LISA. So here's in the LISA, we need to choose any lambda k bar to perform the LISA, right? The starting trial step size. And for the classical amiso, one possibility is, and we usually fix this as a constant. Okay, but in our algorithm, we can use any trial step size lambda bar. And we also suggest here something called a self-adaptive trial step size. Basically, saying that if we have two successful consecutive successful trial step size, then we increase our step size, our trial step size in the third step. Okay, so lambda k minus 2 bar and lambda k minus 1 bar. Then in the next step, we increase the trial step size by any factor gamma greater than 1. But in general, we can do whatever trial step size we wish, because this one is true for any lambda k bar. So this is just one proposal from Phan. Okay, we come to the numerical experiments. The first experiment is finding the steady state of biochemical reaction network. So basically, this is the starting point of our collaboration, where we both the postdoc at the Luxembourg Center System Biomedicine. So I think Phan present this one in Rio Center, in Rio, in Brazil, 6 years ago or something. So we were asking to compute a steady state of a very large biochemical reaction network defined by a dynamical system, dx over dt equal to f of x. And f of x can be written at px equal to cx. Okay, and solving that, which is equal to minimize the objective function phi here, which is px minus cx squared. And where p and c divided by formula, okay, px and cx, where a capital F and capital R is the matrix in the dimensional m times n. M here is the number of molecular species, and n is the number of reversible reactions. So I will not, I don't have slide in detail to describe the steady state biochemical reaction network, because maybe it's not interesting for you. And we can prove that this one is analytic function and it satisfies the Lojasiewicz property. And then we can apply our BDCA to this problem, minimize the function phi of x. So this is the starting point of BDCA, because when Phan be able to write on this problem at the DC function, and the first idea come to our mind when we have a DC function is to use the DCA. But when we apply DCA, it's very slow. And we were thinking, can we somehow accelerate the DCA, because in this case we have both function g of and h are smooth, a smooth function. And because the DCA work for non-smooth as well, so we were thinking what can be obtained if we have both function as smooth. So that come to the idea of the BDCA, where we can prove that the descent direction, the direction dk, which is equal to yk minus xk, is also a descent direction at the new point yk. And here is the computational result for several models. Is the real life model in biochemistry. We have 25 or 30 models. Here I just represent some small model. So on the right column here, you see the ratio, the iteration ratio and the time ratio between DCA and BDCA. So basically it say that how many times BDCA faster. For example, in this first model, equally core, DCA need 5 times more in iteration and 4.4 times more in time. And for each model, we select a random kinetic parameter P defined in biochemistry, and 10 inertial random starting point. And we run BDCA 1000 iteration and DCA to obtain an objective value. And DCA will run until extract the same objective value by BDCA. So this one is a little bit boring, but anyway, okay, here's the comparison where we use the constant step size, the constant trial step size, and the cell adaptive step size. So the adaptive step size version can accelerate the performance of BDCA. For example, in this case, is almost 7 times faster than DCA. So it's the red line is the ratio between DCA and constant BDCA. Okay, it's 4 point something. And if you have a look at the black dot line here, you can see that the adaptive step size have to accelerate the constant BDCA by almost 2 times. Anyway, it is now the BDCA is a part of the Koch-Batoon's box for the biochemistry community. So the paper published in the Nature Protocol, and we have citation almost every day for the application in biochemistry, where the community use this toolbox widely. Here's the second numerical experiment, which is the minimum of sum of square clustering problem. We have Professor Bagirov in Federal is an expert on DC algorithm and minimum sum square clustering problem. So this is an unsupervised machine learning problem. Basically, we need to divide a set of objective A is A1, AN to k disjoint subset we call the cluster. Okay, we need to divide the set of subject to smaller cluster, such that clustering iteration is optimized. So the minimum sum of square clustering is the is an example where the objective function is defined by this formula. And the center of X cluster is denoted by X, okay, which is X1 to Xk. And we need to minimize this objective function with respect to X belong to a matrix from psi m times K. And this one can be rewrite as a DC function, DC programming by G and X here. So G here is strongly convex and smooth, and X is strongly convex but non-smooth. So we did a numerical experiment for a problem of dividing the Spanish cities into 5 clusters. Okay, for 4,000 Spanish city with more than 500 residents. And here's the random starting point within the black point here. So after one iteration, you see that the BDCA send you far away from the starting point, right? Where the DCA just move a little bit. So 1, 2 iteration, 3, and so on. So the red one is the trajectory of BDCA, and the black one is the trajectory of DCA. And after 12 iteration, the BDCA sends you to the critical point, while the BDCA need here 50 iteration to get to the same critical point. Okay. So we also do the experiment with K cluster, where K belong to 5, a set of 5, 10 to 100 cluster. We choose 100 random starting point. And BDCA was stopped when the relative error is less than 10 to the power 3. And DCA run at the same starting point until the same value of objective function is obtained. And it cannot happen for 31 instance. Here we compare the ratio. So here's on the left is the time ratio, which say that BDCA is 15 or 16 times faster in time. And in the number of the iteration is about 17 times. This is the number of iteration. And the third experiment, Phan took n random point m with the normal distribution. Okay. And n belong to the set of 500 to 10,000. And m belong to this set from 2 to 20. We also take the 10 random starting point. The task is to divide this point to K cluster, with K belong to this set from vary from 5 to 100. And this is run until the same value objective function is reached. And just to show again that on average, BDCA was almost 14 times faster than the DCA. The black dot is the average. Okay. The first application is the multidimensional scaling problem, which I like the most. So suppose that we have a matrix, a table of distance between the sum objective. Now at the dissimilarity matrix can be represented by the distance between that point. for example, a simplest example is that if we know the distance from Sydney and Melbourne and Canberra, the distance between the three cities. Now the task is how to represent the city on the map. Okay. So we choose a target dimension P less than or equal to Q. So this has some application in compressed sensing. And the MDS problem is to represent the point in the target dimension P. And here's the objective function. In our optimization model, we need to minimize the stress of phi x star, where Wij is the weight. And here's the discalamity matrix in the target dimension. And here's the real data, delta Hij. And this problem can be reformulated again as the DC programming. Moreover, we can check that C is smooth and X is non-smooth. But just to mention that the subdifferential of C can be computed easily. So in the experiment, we consider the discalamity matrix defined by the distance between more than 4,000 cities of Spain with more than 500 residents. And now including time, including also the Iceland. And because the target dimension is the same with the original dimension, the optimal value of this MDS is 0. And here you see the performance of BDCA and DCA. So the task is to reconstruct the map of Spain. The data is the distance between the cities. And you see that BDCA obtained the optimal value in 120 iterations. Okay. And DCA need 300 iterations to obtain the optimal value. As I already asked a question, how do we choose row? Basically, we just choose a random one. In our iteration, we choose row equal to 1. One of the interesting question is, what is the optimal value of row so that the DCA or the BDCA perform the best? And we cannot answer this question at the moment. Anyway, it's a very interesting question, Johnny.
Thank you very much. Thank you.
Okay, here we have this already. So here you see the objective value, phi of xk. In the orange one is the BDCA, and in the blue one is the DCA. The objective after 120 iteration for BDCA and 700 iteration for DCA. So here's the running time for a random starting point. Okay. With on the y vertical is the running time and the number of iteration, and on the x vertical is the random starting point, and here's the ratio. You see that the BDCA is about like 3 or 4 times faster than DCA. In the last figure, I just show here the behavior of the trial step size. In the green one, if we use the constant step size, on the vertical on the left is the objective value. Okay, so the green is the constant. If we use the constant trial step size, and the orange one is if we use the self-adaptive step size. So you see that there's some peak here, which means that the self-adaptive step size can be increased very aggressively. For example, is here it can be up to 50, okay, and 30, and so on. And in our numerical experiment with the constant, we use lambda k bar is a constant equal to 3. But if we use adaptive step size, is very aggressive. That's why we have a good performance in the orange curve here. Thank you for your attention. And here's some reference. The main reference is the second and the third one. So at the moment, we still keeping developing the BDCA for non-smooth, fully non-smooth K, and hopefully this will be published soon. Thanks again, and I hope to get some question from the audience.
Thank you for the nice talk. And now is the time for question or comment. Yes, if you have any question or comment, please unmute yourself and ask the speaker.
May I ask another question?
Yes, please.
Yeah, please.
Continuing on my previous one about the KL property, I know that this condition is very popular in convergence analysis. There is another one which is also very popular, maybe even more popular, and not only in convergence analysis. It is about error bounds and or equivalently subregularity and stuff like that. In fact, I have a feeling that the KL inequality is actually a sufficient condition for nonlinear error bounds. So what do you think? Can it be that in your considerations, nonlinear error bounds would be enough instead of the KL inequality? Error bounds is a weaker condition.
Yes, thank you for interesting question. I think that is possible, at least for the classical error bound. It leads to the linear convergence.
But this is about nonlinear error bounds. So be cautious.
Yeah, I haven't think the nonlinear error bounds, but I saw some paper, your paper published in optimization, right? I think that is possible, but we haven't tried. But there's connection between KL property and classical error bound. I think the papers were done by Ariane Lewis and Damek Davis or something. I think goes in also. Yeah,
plenty of publications and people are using these things separately. It would be very interesting actually to clarify what is really needed for convergence analysis and other things. Historically, people use KL inequality, but maybe error bounds would be enough. Okay, just a comment. Thank you.
Yeah, Holder matrix superiority or something.
Holder, but you are using this function phi, I think. So it is more general than Holder. But even more general error bound conditions also exist.
Yeah. I think it's interesting to have a look at that. Thank you again for the comment.
Thank you.
Okay, any more questions? maybe I have one questions. Can you control the step size lambda?
What step size lambda? The trial step size lambda bar,
No,
or
I think because in some result you need that lambda k is bounded, right?
yes.
Yes. So can we?
But it's just a theoretical assumption. Practically, it's just a technical assumption where you need the convergence of the you need the sum of the difference between xk plus 1 and xk. So in practice, we need lambda bar as big as possible. I mean, if we have a descent direction, and in principle, we want to go to follow that direction as far as we can.
Okay.
So I don't think it's a problem that we have to bound it or to control the step size lambda bar.
Okay.
So if you see what in one of the figure, the bigger lambda bar, the better performance. You see, you have a look at this one.
Okay.
I have a question, Vuong.
Yeah.
Because any DC optimization problem can be expressed as the difference of two strongly convex functions. So suppose you do not express it as a difference of two strongly convex functions by adding that norm square, can it still what are the disadvantage you will have if you don't make it strongly convex?
That is interesting question. In the convergence analysis, I needed at least strictly convex or for both function, and it's also needed for DCA.
Okay.
And again, this is come back to your question: how do we choose the best role, right? And we don't know. Actually, we don't know how to choose.
Any row, actually, any row greater than 0.
Yes, it's the convergence analysis is true for any row.
Yeah.
So what is your question on this again? Sorry.
My question was that if you have any DC optimization problem, you can always add this row norm x square with 1 and subtract it from the other, so to get a difference of two strongly convex functions. So what I'm saying that in many papers which I have seen, for example, this paper by Akiko Takeda in Japan, so they don't use they are not using a technique. I like this strongly convexity, my part personally.
Okay. I get the point.
So I want
get
to
your
know
point.
what advantage if you have strong convexity and what will be the disadvantage if you don't take the strong convexity.
Actually, we can do it without a strong convexity assumption by adding here. Let me go to the algorithm.
Maybe something with the convergence or
implement. Is here. Here you add a proximal term. You add here 1/2 rho over 2 x minus xk squared. So you add this proximal term. So if G is only convex, we need to add here a proximal term regularization to make it strongly convex. So, for example, in the paper of Akida, they do the same. So, but when you add a proximal, a strongly convex term here, so basically it's applied implicitly the DC decomposition. So in that case, we only need G and X are convex, or even weakly convex if you add here a regularization. but the technique is the same.
Oh, thank you very much.
Thank you, Jody.
Okay, thank you. Any more question or comment? So if not, let thank you for the nice talk again. Thank you for joining us today, all the audience, and hope to see you next week.
Thank you everyone for your attention.